Very good morning to you all. So last class, last two sessions, we were discussed on various fundamentals of thermodynamics, classification of thermodynamics, an important terminology what we used: system, boundary, and surroundings, process, path, cycle, state, process, path function and point functions, and basic properties: intensive property, extensive property, and their units. Example for intensive properties, approaches like macroscopic approach and macroscopic approaches. So that are all we were discussed in the previous sessions. Today we will be continue with the topic called as types of processes. Even though we were discussing the same topic in last class, again I'm going to recollect again with the topic types of processes. So starting with the types of processor, classification of processes, the first process, isothermal process. If you in bracket it put T is temperature, temperature remains constant. Iso means constant, temperature means thermal temperature. So temperature remains constant. Second one, isobaric process, pressure remains constant, P. Then isoporic, volume remains constant, constant volume process. Then S, isentropic process, entropy remains constant. Then enthalpy constant, isenthalpic. Then isosteric, the concentration constant is isosteric. And adiabatic, there is no heat addition or removal. That means no heat transfer from that process is called as adiabatic. So reversible adiabatic process are also known as isentropic process. So that and all we have discussed in the previous sessions. So we'll come to the discussion on the each and every processes and the equation or relation correspond to that processes in that next sessions. So next, one more process that is very, very important that related to thermodynamics, that is called as quasi-static process or QS process. QS process is also known as quasi-static process. So how to define this process? A quasi-static process is a process in which the deviation from thermodynamic equilibrium is infinitesimal. So let I discuss the thermodynamic equilibrium and that coming topic anyhow. So just now, as of now, you just know to understand that deviation from that thermodynamic equilibrium process is infinitesimal. That kind of process is called as QS process. So that means all the intermediate states of the system process, all the intermediate states, series of states of the system passes through all are in equilibrium states. All are in equilibrium states, and they are all in.
Excuse me, sir.
Yeah.
Sir, your presentation is not visible.
That's not somebody told is visible. What about now?
Yes, sir.
Yeah, fine. You would remind me if any issues are there facing in that presentation. Okay, so a quasi-static process in which the deviation from thermodynamic equilibrium is infinitesimal, and all the states of the systems pass through that systems all are in equilibrium states. You can see that piston and cylinder arrangement that is there in the diagram. That is a gas filled in the piston cylinder arrangement. That is example for this QS process. I will explain how the process. So that thing is, we are what is the process in the sense in the system piston cylinder arrangement, we are loading with the number of weights so on that system. So then we are going to remove the weights slowly one by one. So what will happen? The gases inside the system will displace the piston gradually. That's mean if first we remove one weight, then it will reach another next one state. Then if you remove next weight, then next it reaches another state 2. Then again remove that another weight is state 3. Like that, whenever we are removing the weight from that piston cylinder arrangements, that each and every states reaching particular property like pressure P1, temperature T1, V1, volume. Similarly, P2, T2, V2, and P3, T3, V3. Like that, pressure and temperature and volume changes with respect to the removal of weights. It attaining different states, and all the states are in thermodynamic equilibrium as well. They are all quasi-static. That means infinitesimally small. That the variation in the change of states are infinitesimal. That means whenever we are removing the weights slowly one by one, the pressure of the gas will displace the piston gradually. Because of the movement, the piston reaches the different states: state 1, state 2, state 3, state 4, like that, up to the end of the final state. So between the initial and final states, All the states are in thermodynamic equilibrium as well. They are all infinitesimal. They are known as they are all called as the process is called as quasi-static process. On the other hand, if we remove all the weights at once, the piston will be kicked up by the gas pressure. What will happen? This is the unrestrained expansion. But we don't consider that the work is done because it is not in a sustained manner. That means we are suddenly removing the weight. Irrespective of removing one by one weight, it will be reaching the all thermal equilibrium as well as all our the processor or processes infinitesimally slowly occurring. That means infinitesimal slowness. Infinitesimal slowness, very important. Infinitesimal slowness is the characteristic of QS process or quasi-static process. So if you remove that suddenly, this is called as unrestrained expansion. We cannot consider that as the work is done because it is not in a sustained manner. In both the cases, the systems have undergone a change of states. Another example, if a person climbs down a ladder from roof to ground, it is a quasi-static process. On the other hand, if he jumps, then it is not a quasi-static process. So ladder means we have step by step, we will be having the one by one, we will be ladder from the roof to ground. Slowly, he will try to come down slowly. That is slow, infinitesimal slowness. They are known as that kind of process is called as QS process. You can imagine, like one person is on the roof of the tree, he is using the ladder to come down to the ground. So slowly he will come slowly one by one. So first state, second state, third state, like that. Each and every state of the ladder will be he will be attaining the system. That kind of process is a simple example for a QS process or quasi-study process. Suppose if he suddenly jumps directly from the tree to the ground, it is not QS process. That's an example. Same way, you can assume piston and cylinder filled with gases. Remove the applying the load weight or load on the system. We are removing the load or weight slowly one by one. It will attaining individuals in all intermediate states. All are in thermodynamic equilibrium, but at the same time, the process is infinitesimal slowness. So the infinite slowness is the characteristic of the process. That process is called as quasi-static process. So the screen is visible, what I am discussing here?
Yes, sir.
Yes. Yeah. So can you understand what is the process now, I think? So with that, as I mentioned earlier, all the states, all the intermediate states in this process or in this QS process or quasi-static process are all in thermodynamic equilibrium. That means equilibrium state. Then we are going to discuss what is meant by equilibrium state. A system, a thermodynamic said to be in an thermodynamic equilibrium, or a system is said to be in thermodynamic equilibrium state if its properties will not change without some perceivable effect in the surroundings. So that means equilibrium generally requires that all the properties of the system to be uniform. Throughout the system, all the properties should be uniform. They are known as equilibrium. The system is said to be in thermodynamic equilibrium if it satisfies all three, like mechanical equilibrium, thermal equilibrium, and chemical equilibrium. If the system satisfies the three, like mechanical, thermal, and chemical, that contains phase change. So mechanical, thermal, and chemical. Mechanical equilibrium, thermal equilibrium, chemical equilibrium. A thermodynamic system is said to be in thermodynamic equilibrium if it satisfies the all three: mechanical equilibrium, thermal equilibrium, and chemical equilibrium. What do you mean by mechanical equilibrium? There shouldn't be an unbalanced force. There should not be any unbalanced force. Thermal equilibrium, it should be uniform in different temperatures. In chemical equilibrium, chemical compositions are all in equilibrium throughout the system. They are all then only the system is said to be in thermodynamic equilibrium. The system is said to be in thermodynamic equilibrium if it satisfies thermal equilibrium, mechanical equilibrium, and chemical equilibrium. Examples: water flows from a higher to a lower level. Electricity flows from a higher potential to a lower potential. Heat flows from a body at higher temperature to the one at a lower temperature. Mass transfer occurs from higher concentration to a lower concentration. Can anyone distinguish under this all this under this all the examples? Can you distinguish this mechanical and chemical and thermal equilibrium, or all are in thermodynamic equilibrium? What's your answer? Anyone try to answer for this question? What are examples given are in thermodynamic equilibrium or specific equilibrium only attained in these examples? Anyone? try to answer for this question. Can anyone answer for this question? Whether the examples given above are all related to thermodynamic equilibrium, all are only related to only thermal, or only to mechanical, or only to chemical.
Sir,
Yeah,
all of them, I think.
all are.
Like, it is in mechanical thermal phase and chemical equilibrium, like all four.
Yeah. So water flows from a higher to lower level. Water contains some chemical composition, higher water. So mechanical work also takes place when you flow from higher level to lower level, and chemical composition also can change, and the temperature correspond to the level of pressure. So like that, heat flows, higher body at a temperature, thermal equilibrium, mechanical work will done, and it should not be any unbalanced work. So whenever heat is generated with respect to a body and all, it can react with generating some chemical changes also if your body is in temperature. So like that, the system, thermodynamic system is said to be thermodynamic equilibrium if it satisfies all three, mechanical, chemical, and what they call mechanical. Then only it is said to be thermodynamic equilibrium. So again, apart from between the system and surroundings, if there is no difference in pressure, they are known as mechanical, they are unbalanced force. Potential, electric equilibrium, is concentration of species equilibrium, temperature, thermal equilibrium. No interaction between them, they occur, they are said to be in equilibrium. See, if there are no such changes or no interaction between the system and surrounding occurs, then the system is said to be in thermodynamic equilibrium. So next is the definition of temperature. So temperature is a property of the system which determines only the degree of hotness, how much hot that system is in that, the property of the system, temperature is there in the system, how much hot it is, that is the temperature. Temperature is a property of system which determines the degree of hotness. What about the temperature? It is an intensive or extensive property. What about the temperature, whether it is an intensive or extensive property? Anyone? The dependent of mass, independent of mass?
Sir, extensive.
Is whether the temperature independent of mass or dependent of mass?
Sir, mass dependent.
Depend.
So temperature is pressure, volume, and temperature are
Mass.
intensive or extensive? Find out and tell me. Okay, just recall the topic. Okay, example: a hot cup of coffee is at high temperature, then a block of ice. So block of ice is low temperature, hot coffee is high temperature. That means the degree of hotness. The temperature is a property of the degree. Temperature and heat is not the same. So the temperature is the degree of hotness. How much heat the temperature is? Sorry, that property of the system is. So hot copy of coffee is, hot cup of coffee is the temperature, higher temperature, and a block of ice is at the lower temperature. On the other hand, ice is hotter than the liquid hydrogen. Again, if you go for liquid hydrogen, ice is melted and it becomes hydrogen. So ice is hotter than liquid hydrogen, something like that. So temperature, thermodynamic temperature scale is under evaluation. So what we have now in only on empirical scale. So what is the unit of temperature? What is the unit of temperature?
Kelvin.
Kelvin, yeah. So why we are obviously are using Kelvin rather than using Celsius? What is the difference? That question asked by Dr. Vasudevan as an assignment. Do you have the idea about absolute scale, absolute temperature? Any idea about absolute temperature? So these are all basic. Whatever the assignment question given to you, all are very, very basic, fundamental related to physics and chemistry. That's why it's given to you to find out, to understand the thermodynamics. Just you wanted to recall the base. That's why he gives the assignment to you. Just follow the assignment and submit to him. Okay, as per their instruction. So next is coming to zeroth law of thermodynamics. So zeroth law of thermodynamics is nothing but two systems are said to be in equal in temperature. So that means equilibrium, thermal equilibrium. When there is no change in their respective observable properties, when they are brought together. When two systems are Equal in temperature, that means equilibrium, temperature, thermal equilibrium, when there is no change in the property, aspectal properties, when they are brought together. In other words, when two systems are at the same temperature, they are in thermal equilibrium. They will not exchange heat. That means there won't be any exchange of heat between the system and surrounding of the system. Both the systems are in thermal equilibrium. So coming to zero law thermodynamics, if two systems A and B are in thermal equilibrium with a third system, say C, separately, that is A and C are in thermal equilibrium and B and C are in thermal equilibrium, obviously then they are in thermal themselves, therefore A and B also will be in thermal equilibrium. So it means A and B, B and C, C and A. So when two systems are thermal equilibrium, obviously the third system also in thermal equilibrium, but thermal equilibrium, not thermodynamic. That is very important. They need to be not to be in thermodynamic equilibrium, but it should be in thermal equilibrium. So that is measurement. The zero law thermodynamics is the base for the temperature measurement. Wherever measuring the temperature, this law is governing. This, for an example, you are using a what I call temperature measurement system, thermometer, flask. So that are all temperature measurement systems, measurement kind of system. So that area, when the two systems are thermal equilibrium, obviously, if the third systems are interact with the system, thereby A and B in equilibrium and B and C in equilibrium, automatically what will happen? A and C are also in thermal equilibrium. That is called as, that law is zeroth law of thermodynamics. State, you may expect to get the answer first in state zeroth law of thermodynamics. There you have to explain when the two systems A and B are in equilibrium and B and C are in thermal equilibrium, and then A and C also will be in thermal equilibrium. It is not to be in thermodynamic equilibrium. There may be chemical change, there may be mechanical change, but temperature remains. Yeah, temperatures are uniform. Some are uniform or equal. And they are called as what I call zeroth law of thermodynamics. Let us say temperature of the system is TA, a system A is TA, temperature system B is TB, and temperature system is TC, correspond to A and BC respectively. So what is the thing? A and C are in thermal equilibrium, that means TA is equal to TC. Similarly, B and C are thermal equilibrium, TB equal to CC. Consequence of zeroth law, A and B will also be in thermal equilibrium, that means TA is equal to TB. So all the temperature measurements are based on this zeroth law of thermodynamics. Since A and B, B and C, A and C, B and C, obviously A and B are in thermal equilibrium. So this means three systems, two are in equilibrium with third one is equilibrium with the other two. That very important, thermal equilibrium or thermodynamic. Temperature alone are in equal. Temperature all alone equal. TA equal to TC, TB equal to TC, and TA TB equal to TB. So this is the measurement. This is the first zeroth law is the base for all temperature measurements on this zeroth law thermodynamics. Next, coming to work and heat. So these are all not at all new to you. We already crossed this topic in your science and school level and physics and chemistry and all the subjects. Anyway, we are again recalling again as a fundamental work in physics. If you go for physics, if we have to define work, it is a measure of energy transfer that occurs when an object is moved over a distance by the application of an external force, at least part of which is applied in direction of the displacement. So if you go for positive work, that means work is done by a system when the sole effect external to the system could be reduced to the rise of your weight. Similarly, heat, we go for define the heat. Heat is the energy in transition between the system and the surroundings. What is the reason? By virtue of the difference in temperature. So by the application of difference in temperature, the transition in between the system and surrounding, that energy is nothing but heat. So heat is the energy in transition. So there's a difference between temperature and heat. So heat is the temperature is the just now we discussed. What is the temperature? Anyone? What is the temperature? These are the one of the assignment question given to you. What is the difference between heat and temperature? Whether it is same or not, like that he was asked. What is the temperature? Anyone? Temperature is the property of the system which determines the degree of hotness, whereas the heat is the energy in transition between the system and surroundings by virtue of which temperature difference. So example, heat to work. If you are having thermal power plant, the thermal power plant, what is objective is to generate power by using thermal plant. So thermal power plant tends to give some temperature changes, heat. The heat is meant for generating power. The conversion is heat energy to power. That means it is heat work. Similarly, work energy to heat energy, refrigeration. So we are doing some work to generate the exchange heat, changing the temperature in the range of cold. That is called as refrigeration. That is the example for work to heat. The sign conversion, what done by the system is positive. For an example, the system is, if you assume the system is there, we are doing work done on by the system, that is positive. What done on the system is negative. Obviously, work and heat in direct proportion. That means heat given to the system is positive and heat rejected by the system is negative. So positive, negative. Heat given, heat rejected. Work done by the system, work done on the system. Positive, negative, positive. Heat and work. If it is positive work done, then heat given is positive. Work done on the system negative, heat rejection is negative. So a different form of work interaction. So the work may be in the form of expansion work, expanding the gases, expansion of the gases, compression work, compression of the gases, displacement work, pressure and piston displacement. Displacement of the gases because of the movement of the applying load on the system, pressure application. What will happen? Removal and applying tends to have expansion compression that displaces the gases and the piston moved up and down. That is called the piston displacement work. Then work done on elastic solids, then work of polarization and magnetization, work of a reversible chemical cell. If you are using chemical cell, there will be a form of chemical energy to work at. Similarly, work in stretching of a liquid surface. So these are all example or work interaction examples. Heats. All temperature changes need not be due to heat alone. Example, friction. All heat interaction need not result in changes in temperature. That means condensation, evaporation. Condensation is liquefaction process. Condensation is this process. It tends to condense into liquid. It becomes liquid. Evaporation, liquid into vapor. All interaction need not result in change in temperature. Similarly, all temperature changes need not due to heat alone. That is the friction. So coming to the PD work, pressure and volume work. PD work is pressure and differential volume. dV is change in volume. So as the same example, piston displays piston and cylinder arrangement. You see there inside the piston filled with the gases, or inside the cylinder is filled with gases. The cross section area of the cylinder is A. So that the length of the cylinder, the piston initially is like L. Then because of the movement of the piston, by applying the pressure P in this direction, tends to move the piston to from initial position to another position from L to DL. The change in the length is DL. Again, we further move applying the pressure. Again, it moves to the another position. Again, change in that system. Because of that, volume changes. So the volume changes occurring with respect to the piston cylinder because of that pressure applying. The first pressure applying the state 1 to another state 2, again applying state 2 to 3, like that state change of states occurring. Similarly, gases displacing the piston inside the cylinder so that the change in volume occurs. So between 1 and 2, it is a PdVP pressure and volume diagram. The volume is V1 and volume is V2. So if you are increasing pressure, so that is the what is the straight line indicates that increases. Then that curve, that varying the polytrope, that process varying with respect to the case. Then it reaches the volume 2, P2. The pressure correspond to the y-axis is P1 and P2, and the volume correspond to the y-axis is V1 and V2. Under that pressure volume curve, that is known as PdV work done. The work done under that curve is W. So W can be given between the limit 1 and 2 with respect to the change in volume V1 to V2 correspond to the pressure application. So that way, the pressure correspond give the idea about pressure and change in volume as the work is that the entire work is called as piston displacement work is known as PdV work. Is otherwise known as displacement work. So as you know, the force exerted by this system of the piston with respect to cross section area is given by F is equal to P into A. So what done? How to find the work done? Work done is the force into distance or force in displacement. So the W work done is given by the change in work, that is dW. The change in D is differential form of work done is change in work. So change in work W dW is equal to F into dL. So change in length is dL, F is the force. So again substituting F equal to PA here, then again P into A into dL. So A into dL again, what is the area into change in length? That is the volume change. So thereby it is dV. So W can be given as dW is equal to PdV. So if you want to go for a system with the changes between the system state 1 to 2, then how to integrate, how to evaluate the net work done by integrating the work done. So the del W is equal to, or dW is equal to integral of this work done. Integral dW is equal to integral PdV between the limit 1 and 2 as volume 1 and volume 2. So actually it is V1 to V2 integral V1 to V2 into pressure P into dV. So with that only we are going to discuss on this different processes PDV. Based on PD work, we are going to discuss everything in that forthcoming units. So this PD work or discipline work is very important. The change in that volume with respect to change in the length, and the change in volume correspond to the area and length will give the idea about change in volume. Pressure exerted by the on the gas is P. With respect to the pressure P, with respect to the volume, the integral limit of D1, V1 to V2 of dV will give the idea about W integral PdV. So by using this, we are going to discuss various processes in the forthcoming units. So where P is the pressure and V is the volume. So see the diagram. So these are all the different possible processes as I mentioned earlier. N equal to 0, if you put what is the thing, if n equal to 1, what is the thing, if n equal to infinity, what is the thing like. So we'll be discussing all the processes in the next unit, next session. And that means PV work, PV raised to n equal to constant, PV equal to gamma equal to constant, P is equal to constant, V is equal to constant. So that is very simple based on n equal to 0, n equal to 1, between n equal to n infinity case. So between 0 to infinity, and in between 1 also, how that each process varies. They are known as possible process, like constant pressure process, constant volume process, constant what I call adiabatic process, then isentropy process, and all we'll be discussing in this forthcoming units. So that will be what discussing here. N equal to 0. If you put P raised to n equal to constant there, if you put n equal to 0, what will happen? N P V raised to 0 equal means 1. So P equal to constant. That is the first one, like that, constant pressure. That means volume 2 is greater than volume 1. We put n equal to 1. That means pressure 2 is less than 1, volume 2 is over down. That is again expansion. Again PV constant. That is isothermal. Then n equal to infinity. Again PV raised to n equal to constant, n equal to infinity. That is constant volume process. P2 less than P1. So like that, each one process given by the general expression P raised to n. See the diagram, volume changes, how it occurs. Gas filled the cylinder, pumped by the applying load, pressure, then moving the cylinder piston movement tends to cause the variation of the change in volume, thereby giving work done. One is the compression, one is the expansion, another one is pressure constant process, another one is P raised to constant, and another one is P raised to n equal to constant. So these are all the thing of what I call the general work done case. So done in the system due to wire stretching. For an example, stretching of a wire, so the opposite direction, therefore it is dW minus FDL. So if you go for electrical energy flowing in and out of the energy in the work, that is dW is equal to minus EDC. So minus E into L into dt. So the length of the wire, stretchy wire with respect to time, the change in that temperature and other power voltage and all, that is the case. Similarly, stretching of the liquid surface tension, sigma dA. Sigma is surface tension, dA change in the area, and dW what is equal to. Again, it is show film or stretch through the area, liquid solid surface, opposite direction. Again, it is minus sigma dA. Similarly, minus EL into dt. So these are electrical work, surface tension on stretching of liquid wire as well as stretching of wire. So these are all the different forms of work. So this about the discussion on work, the heat, thermodynamic equilibrium, different processes and different forms of energy, work energy, different form of work and various process. The next session we are going to discuss based on one more thing we discuss is QS process, quasi study process. In the next session, we will be discussing the various processes on with respect to the system, then first law of thermodynamics, and some numerical on this. Then one more topic we will be having a study plan. It's all about the unit number 1. Okay, so this are all about today's session on the topic called as quasi-static process, QS process, quasi-static process, and what I call different process types of processes, and the work, heat, interaction of work, interaction of heat, sign conversion of energy and work, heat and work, both are energy forms. And then like what I call, just now we discussed different form of energy, stretching of wire, liquid surface on a surface or electrical energy changes. So all example for the work transfer. Addition to that, we'll be having the discussion on the PD work called the displacement work, piston displacement work. So based on the piston displacement PD work only, we are going to discuss the entire work processes, and we are going to apply this first law of thermodynamics to these various processes in the forthcoming units sessions. So as of now, one more topic we discuss is zeroth law of thermodynamics. That because before that we discussed on temperature scale, that we had one word absolute temperature. So temperature in terms of Kelvin. So that is absolute temperature scale. Then difference between temperature and heat as well. The zeroth law of thermodynamics, that is a basic for measurement of all temperatures. So these are all the topic what we discussed in today.